both Yuval and I work for NVIDIA. And my job at NVIDIA is to build the best tools that I can offer for developers.
Hi everyone, my name is Yuval. I'm a solution architect at NVIDIA, and I take the tools that Yaki produces and go out and actually throw them at unsuspecting customers.
And since we see repetitive patterns in clients, we thought it's about time to give a practical guide for how to use deep neural network training apps and actually optimize them. So a typical scenario. You are a client, let's say, of NVIDIA, Intel, AMD. You buy a brand new machine, a bunch of GPUs which are shiny. Everything is nice. You install the operating system on the machine. You write, you install your typical DNN training software stack like TensorFlow or PyTorch, and you write your training program and you run it. And then you see a few things. First, training is very slow, and usually the utilization of your GPU is very, very low. And then you start thinking, what's going on here? So looking at it, it seems quite obvious. You have your Python program. You have the framework, which should do all the magic for you. It should handle the CPUs, the GPUs, all the networking, the PCI Express, and things like that. And you don't really know what's going on. So in theory, it's nice. But in practice, if you would like to get the maximal performance out of the system, the framework needs to work like a conductor of an orchestra. Everything needs to be tuned. So you can read data from, let's say, the network and download it to the SSDs, and then move the data from the SSDs over the PCI Express to the system memory, and then do some serial work on the CPUs, and then some parallel computation on the GPUs. And if you don't feed the CPUs fast enough, and if you don't feed the GPU fast enough, they will be just waiting and doing nothing, and this is not what you would like to do. So it looks like an easy task, but it's definitely not. So what do we do? Why doesn't the framework handle the system correctly? So the frameworks have many knobs. Some of them are environment variables. Some of them are the API of the framework itself and the large amount of parameters that the API can get. Some of them is the way you structure your network. And the first thing you need to do is to get familiar with all the knobs that you can turn on and off and do all kinds of things using your networks. And I can assure you that out of the box, these knobs are not set correctly to your system. And this is usually the main problem. And actually, some of the knobs have default values which are not that reasonable. So you need to know the knobs, and eventually what you need to do is to tune the knobs correctly to get the maximal performance out of the systems, which is nice, but how do we do that? So what you should do is you should use a profiler, of course. If you don't use a profiler, your system is something like a black box that you push something into it, something happens, but you don't really know what's going on. So you should use a profiler. You should first run the application under the profiler and then look at the results. Usually, at least at the first iteration, it will be very easy to see what's going on. Someone is waiting for someone, some unit is not really utilized, and after you know the problem, you need to look for the knobs that control this unit or control this behavior and try to play with them until you get the desired performance. So you profile, you see the results, you optimize, you play with the knobs, you change things, and then you need to run again under the profiler. And there are a few options. One option is that nothing really changed, and then you need to go back to the drawing table to figure out what did you do wrong. Another option is that, it changed, performance improved, and then usually the bottleneck moves to a different area. And then you need to do this circle a few times until you reach the desired performance or until you run out of time. So this is the theory. Let's go to the expert and let him show you a real-world profiling session.
Okay, so thanks, Yaki. And what we're going to do now is we're going to go through a sample profiling session where we'll show you a very, very simple deep neural network application using PyTorch. And going from there, we'll show you how basically we need to apply all of this methodology that Yaki has just discussed. So the hello world of neural nets. If you've done anything having to do with AI and neural nets, you're familiar with the MNIST dataset. Just in case you're not, these are 60,000 28 by 28 pixel images of handwritten digits. And our task, what our neural network is going to do, is it's going to take such an image and then tell us what the digit. So for instance, we're going to show it the picture of a hand-drawn 4, and the network should output the digit 4. So what do we have in this simple program? So as we said, simple DNN training program written in PyTorch. The reason we use PyTorch is primarily for explanatory power. It's just easier, in my opinion, to actually show you a program written in PyTorch, but everything that you'll be seeing here today is equally applicable to PyTorch as well as TensorFlow. And in fact, we'll show you a small TensorFlow example a little later on and kind of discuss some of the details. So we're going to be doing training in batches and epochs. And I'm assuming everybody's familiar with those terms? Okay, cool. So we'll be working in batches and epochs, and we'll be structuring our program in terms of the following steps. And this may seem kind of overkill that I'm emphasizing this, but in a moment you'll understand why. So first thing we're going to be doing in each one of our batches is we're going to copy data from the CPU to the GPU, or in more technical parlance, we're going to copy data from the host to the device. Next thing we're going to do is we're going to do a forward pass where we feed the data into the network and get a prediction. Finally, third stage is we're going to run a backward pass where we get the prediction and correct the errors of the network, and then we're going to repeat this many, 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 many times. So in fact, this is the program. As you can see, there's really nothing scary or weird about this. This is where we iterate through the batches. In this piece of code, what we do is we actually do the hosted device copy. Here, we're doing the forward pass, and here we're doing the backward pass. And finally, we have a small diagnostic piece of code that gives us some statistics every once in a while. So really nothing special here. Okay, so we took this program and we ran it on a completely new system, has 4 Volta GPUs, so a very powerful system, and we got 89 seconds to completion. So for something this simple and a GPU that is so powerful, 89 seconds, something is wrong. This is not what we expected. This is not what we expected in absolute terms, and it's definitely not what we expected in relative terms, as you'll see in a little while, where we improve this program and actually get it much, much lower. Okay, so coming back to this, what we're going to do is we're going to run the application under the profiler, and we'll see what profiler in a second. We're going to optimize our bottleneck. And in fact, when we talk about optimization, a key part of the process is actually locating the optimization, and we'll focus on that for a little while as well. And then finally, we'll inspect and analyze and tune the program, and then it's possible to just repeat. Right, so how do we go about and actually profile our network? The tool we'll be using is a tool out of NVIDIA called the Nsight Systems Profiler. This is free. You can go ahead and download it. If you're using NVIDIA NGC containers, then it's built into the container. You don't have to do anything. The speciality of this profiler is that it can handle both CPU and GPU metrics. So you're able to actually watch the interaction of a program and see what the CPU does, see what kind of CUDA and cuDNN calls are being made, and finally, what actually happens on the physical GPU. So it's a complete systems profile that allows you to trace from the code and all the way down into the physical hardware. Okay, so this is how we go about and run it. I'm not going to go into all of the small nitty-gritty details, but basically what we do is we let the program run for 10 seconds, make sure that it warms up, that it gets into its normal operation regime. Then we sample for 15 seconds. This is enough data so that we can actually figure out what's going on. Obviously, these numbers are going to vary based on your model, on your data, and a whole bunch of additional parameters. Finally, we ask the system to profile certain kinds of data. So OSRT is OS runtime. So what does the CPU do? cuDNN and CUDA, obviously calls that take place on the GPU. And finally, NVTX, which is actually something really nice. It's kind of an annotation framework, and we'll see how NVTX is actually rather critical to the process that we're going to be doing today. Okay, so at this point, we'll be leaving our slides behind, and Yaki will start driving the profiler. So this is Nsight. As you can see, we have a timeline, and we have CPU, we have CUDA calls, and we have actual, where is it? Here. And we have actual calls that take place on the GPU. So if Yaki now zooms into the operation, so we can see up here the relative timescales, and what we can see is that the GPU, this is the physical work being done on the GPU. We can actually see that there's a block of operation, then the GPU goes idle, then there's another block, then the GPU goes idle. And in fact, if Yaki can now just measure those blocks, right? So how long is this idle time? So that's 182 milliseconds. And how long is the active time? Oh, sorry, yeah, 2.2 milliseconds. And the active time?
The what?
Yeah, the time where it's not idle.
About 5 minutes.
5. So we're talking in the vicinity of about 40% of our GPU time is idle. So looking at what's happening now, we can see that if you notice that during the time that the GPU is idle, the CPU is actually waiting on a semaphore. Okay? And we see that the CPU is running some kind of code. Then it's waiting on a semaphore. Then, if down here, if we can just get this pop-up out of the way, yeah, then we're seeing some CUDA calls that are being executed, so CUDA API calls. And finally, once we start this, then the GPU gets to work. So it's pretty obvious from this system that we're being bottlenecked by a certain kind of CPU operation. We're running some kind of code, we're waiting for a CPU operation to complete, and only then are CUDA instructions being assigned and being run. So the next stage we have to do is we actually have to figure out what's going on. Can you just go back for a sec? Is actually figure out what's going on in this interval. And in order to do that, what we'll need to do is we'll need to go back to our code, to our PyTorch code, and here we'll use NVTX. And Yaki, could you make the font just a bit bigger? Perfect. So remember, I was talking to you about epochs and batches and forward passes, and I was being extra dramatic about it, although it's pretty obvious. Well, NVTX stands for NVIDIA Toolkit Extensions. It's an annotation technology that allows you to put in certain markers inside the code, and Nsight can pick up on those and actually show you connections between specific blocks in your code and things that go on at the API and the physical hardware level. So we have an NVTX range. Notice the range push and the range pop. And we call this one copy to device. And what it does is it encapsulates the device to the host to device copy. We then have the forward pass, and if we scroll down a bit, we'll have the appropriate backward pass. It's here somewhere. Okay. So that's the general idea. Now we run our profiler again. This time, we actually look for the NVTX markers. So we're going to notice the exact same thing. And now when Yaki opens the NVTX tab, notice that we can look at our code, what it does for a specific epoch, and then for a specific batch, and for every single operation inside a specific batch. And if we look for this little piece of code that we saw earlier, notice that this fits in perfectly with the data loading piece of the code. And now it's pretty clear who the culprit is, or what the culprit is. So what's going on here? We have a CPU making a call to the disk. Why does it do that? Basically, it wants just to pull out the data and prepare a batch which we will now feed to the GPU, and the GPU will run the forward and backward pass. So the CPU issues the code to read from the disk. This is our semaphore. We're waiting for the completion of that I/O operation. At this point, nobody's doing anything, right? This is physical hardware. This is the disk that's actually doing something. Once we have that, we'll do the copy, and only then will the GPU start running. So all of this time is actually time that we waste. And we can actually do something to make this much, much, much faster by going back to our neural network framework, in this case PyTorch, and looking for the relevant knob that we have to tune. In this case, the knob that we have to tune is the num workers parameter in the data loader. So rather than have the CPU only pull up a single batch at a time, what we want to do is we want to have it pull multiple batches at a time. Make sure the CPU is constantly preparing new batches in order to feed to the GPU. The kind of like graphical image that you can think of when you're doing this is that the GPU is this monster and you have to keep feeding it all the time. If anybody's seen Little Shop of Horror, right? Chanut Ktana U'Matrifa, and there's a scene where the plant goes, "Feed me, Seymour." Yeah? That's what we're talking about. That's the GPU. It's only slightly less cuter. Great. So at this point, we want to go back to our code, and we want to look for the relevant knob in PyTorch, which we want to tune, and it's over here. And rather than have one worker, we now want to switch this up to as many as is relevant to our system. And this is where it gets a little more tricky. Why? Because it depends on the amount of CPUs that you have. It depends on whether you have SSDs or regular hard drives. Depends on whether you're doing a distributed call from something like MinIO, or if you have this nice network attached storage, or if you have something distributed like Ceph or Gluster. Depends on a gazillion different factors, and this is where intuition, art, and experience come into play, and it's up to you to tune this parameter. But assuming that 8 is the right number, we now profile our program for the third time. And we will look for the same exact pattern. What's important to mention is that we're not going to get rid of this pattern, right? So the CPU always has to read data. The only question is, are we able to do this piece of code? Are we able to do this data read much faster? And can we have the CPU not be idle, and as a result of that, the GPU not be idle? So zooming back in, it's very easy to localize ourselves by using NVTX ranges. Zooming in. Yay. And here we go. Data loading is now down to 44 microseconds, and CPU is completely swamped. It's constantly working. Anybody noticed how long our data load took when we were looking at our first iteration? Nope? Then Yaki will show us. So we're not telling, we're just going to show. Yeah, almost 4, as compared to 44 microseconds. Quick math, that's a 40x improvement. By doing what? Tuning our framework. Okay, so this is as, shall we say, basic and naive and banal as it seems. This is something that I encounter with a huge amount of my customers. So everybody knows about this. Everybody knows that you have to do your I/O and make sure that the GPU is correctly fed. But very few of the people that I work with are actually able to quantify this and understand what the right number of workers will do. If it's too low, then the GPU stays idle. If it's too high, then the CPU constantly keeps doing context switches and thrashes, and the GPU as a result will stay idle. So it's either too high or too low, and it's up to us and use tools like Nsight in order to tune all of these parameters. So this was something very, very simple. It would take you approximately 1 hour to go through this process had we not done this together now in 5 minutes. But this is literally a super low-hanging fruit that can improve your training out of the box. So what did we do? Okay, so we ran the application under the profiler. We used Nsight, and we recorded CUDA, cuDNN, OS, and NVTX ranges. We then looked and recognized where our problem was. We changed sorry, it goes the other way around. Obviously we looked, and then we optimized the code, and we tuned the knobs for the frameworks. And presto, just like that, we improved our data loading time by a factor of 40. Okay, so this was PyTorch all the way. And as I said, we showed this in PyTorch primarily because it's very easy to understand the code, even if you're not a seasoned PyTorch programmer. What happens with TensorFlow? Obviously, we would like to have the exact same capability for TensorFlow. And what happens in TensorFlow is that, at least in versions 1.x, you write your code in Python, but the computation graph is actually composed of nodes that are written in C++. So we have an open source project called NVTX plugins, and actually this was developed at NVIDIA Israel, and this allows you to have the exact same capability of NVTX inside of TensorFlow.
So it's a package that I download and install.
So yeah, the question is, this is a package that I download and just import into my code, and that's correct. So you still need Nsight because in order to actually look at the timeline and see the results. And this is what a TensorFlow graph will look like. All of these layers are operations that are written in C++. And what we need to do is we need to add in additional nodes for NVTX. These nodes don't actually do anything computation-wise. So if you're thinking about what happens to the gradient, it just goes through. So as far as gradient processing is concerned, they're completely transparent. What they do, in fact, is allow Nsight to understand that what goes on, the operations between these two ranges, between these two ops, between these two nodes, are something that we would like to call by a specific name. And this is the relevant code in TensorFlow. So notice that we do this import statement. As I said, this is what you need to do with the package. You then initiate your start operation. And then there's this context that you need to make sure goes through your operations. So not quite as nice as PyTorch, but I think that this is reasonable.
There are also function decorators. There are also function decorators that you can use if you find it more easy. And we put it, it's both open source on pip, so you can do pip install, NVTX plugins. It's very easy to get this code.
Yes, so the question is, do we have the same interface for Keras? And the answer is yes. And this is what it would look like under Nsight. So a small point that we need to make sure if you're using TensorFlow. So notice that we actually have two tabs. Okay, so the first one is called default. And the way NVTX is implemented for TensorFlow is that every single operation in TensorFlow actually emits an NVTX range. NVTX operation. So if you have this hankering for seeing exactly what TensorFlow does under the hood, all of the small details, knock yourself out, open this tab, and get ready for 3 weeks of actually digging in. It is nice to see, but it's usually not what we're looking for. And instead, we have this, the forward domain. And each one of these guys is called a domain. So our NVTX ranges are in a domain called forward. The default domain is something that we're usually not interested in. And obviously, you can generate as many domains as you're interested in. So if you want to organize your code by algorithm or by author or by phase of the moon or what have you, it's completely up to you. And Nsight can show you all of these together. And notice that, in fact, this looks very similar to the same experience we had with PyTorch. Okay, another tool that we're interested in showing you is something called DLProf. DLProf is an add-in for TensorBoard, and all of the data that you saw earlier can be imported into TensorBoard, and you can have the same kind of interface with a small caveat. Right now, the only domain supported for DLProf is the default domain. So what does TensorFlow do under the hood? But very soon, we're going to allow additional domains to come out as well. So this is a matter of weeks?
They're working on it.
No, working on it. Cool. Okay, another view of DLProf where you can actually dig in deep into all of the details. Okay, so this was very, very low level, but if we now go from 10,000 feet to maybe 50,000 feet, what do we want to do if we want to improve our training? Things that you can do that are not specific to a model or a network, but rather things that are more systemic. Reason we want to do this is because we have a lot of data. We want to train multiple times per day. We want to have more iterations for our data science teams and basically just have a much faster time to market. So as we said, and in fact, the demo that we showed here today has to do with the upload and the download of data into the GPU. This is one of the most critical things to get right. And from experience, I can tell you that a lot of GPU users don't get this done right. One of the most important things to remember, and if there's one thing that you want to remember from this slide, is that the memory and compute subsystems are completely isolated. So while the GPU is churning away and doing compute at 100% utilization, it's perfectly possible to upload the next batch or to download the results of the previous batch. You will not disturb the GPU. It's completely separate hardware. Make sure that you actually use this correctly. As we saw, make sure that whenever the CPU is ready, it's preparing multiple batches. Again, the GPU is super hungry. Feed it all the time. And this actually is far more important if you're using technologies such as NVLink, which is a specialized bus for GPUs to talk to one another. So rather than have GPUs talk through the same PCI Express bus as the CPU and all of the other devices, In specific systems, you have another bus called NVLink, and that allows the GPUs to talk to each other and leave the PCI Express bus only for data loading and unloading. So in that case, it's even more important to make sure that the CPU feeds all of the GPUs with enough data.
But that really is a so it's not available in the low end GPUs.
Yeah, so no, NVLink is not available with 1080s. 1080s are Pascal architecture, and NVLink is available, well, it is actually available with Pascal, but only with Tesla cards, as opposed to the GeForce cards, which the 1080s are. But yeah, Volta doesn't have consumer cards, but Turing does, so 2080, and NVLink is available for the 20XX series, so 2060, 70, and 80, but it's limited to only 2 devices. So you can do only 2 devices that are NV-linked. For the consumer cards, obviously it's not an issue on Teslas and Quadros. Oh, and of course, DALI, forgot that. So DALI is a library for doing pre-processing on the GPU. So if you're doing computer vision or any graphics-oriented work, then a lot of the stuff you'll be doing during your pre-processing phase when you're preparing your batches is things like cropping, changing colors, rotating, flipping, those kinds of operations. Processing images on the CPU is efficient, but if you could do that on a GPU, it would make your batch preparation even faster. You would leave the CPU more time to do I/O, and you would use your GPU better. You would increase your utilization. And that's exactly what DALI is for. So that's also an open source project. Have a look at it. And it's available inside the NGC containers out of the box. OK. For Volta and Turing, so Volta and all of the 20 whatever series, we also have specialized hardware called tensor cores. Tensor cores are able to do this operation where it multiplies 2 matrices and then adds a third one. It can do this in 1 clock cycle for 4x4 matrices. So an optimized path for doing FP16 math. So if you're able to use mixed precision for your models, mixed precision means some of your layers will be held in FP32, other layers will be in FP16. And what you'll be able to do is you'll be able to use this specialized hardware, and you'll take less memory, you'll run faster, and something that is just as important, your memory bandwidth, the amount of usage that you'll be applying to the GPU when you're uploading or downloading data will also be reduced, which will all lead to lower utilization of the GPU, which in turn means you can increase your batch sizes. So optimal batch size is actually the key here, and it's up to you to tune. There are no hard and fast rules for what models use what batch sizes. It also depends on your specific use case and on your specific data. Fortunately, there's a tool called Automatic Mixed Precision available for both TensorFlow and PyTorch, and allows you to do this automatically. Okay, third best practice. At this point, we're talking about you have massive amounts of data, your network is super optimized, and the only way to go faster is go into hardcore parallel processing, which means using multiple GPUs. Notice that this is different. Okay, this is not the same thing as running multiple processes on the same GPU. If you have to run multiple processes on the same GPU, there's a tool called the multi-process service. Have the link down here. It's nice, it's useful, but we're not going into details on that just now. But if you do want to use multiple GPUs, as I said, if you just want to train faster, if you want to have multiple iterations per day, and so on and so forth, then the most important thing to do is make sure that you use the proper interconnect. So NVLink and similar technologies. For large training jobs, if you have massive training jobs, then what we would recommend is that you use a DGX. DGX are a class of machines, and they're optimized for this kind of training. And in fact, we built these because that's what we use in our own data center. And also, don't try to roll your own multi-GPU frameworks, chances are you won't do it correctly. You'll have some kind of bottleneck that you won't be aware of if you know what the TensorFlow parameter server approach is. It's suboptimal for these kinds of machines. So use something like Horovod. Horovod is, again, an open source framework coming out of Uber, but this can get very close to the theoretical limit of what is possible with multi-GPU, given Amdahl's law and all of this relevant physics. And finally, what do you do when you have to do inference? Okay, you trained your model, and now we have to deploy it into production. So two things that we can do, either software or hardware. Let's start with the easier thing, which is hardware. And there are special class of GPUs that are intended for inference. So if you use a very high-powered GPU like the V100, which takes up 300 watts, needs a lot of cooling, and so on. So the T4 is actually something that is much smaller, takes up about 70 watts, and is far less expensive, and it's ideal for doing inferencing as opposed to training. That being said, it can do training, right? But it just wouldn't be the ideal GPU for that. What you want to do with software is once you have that model ready, it's a model that is intended to be run in development frameworks. How do you then take that code and make improvements to it, make optimizations? And for that, we have a tool called TensorRT. So if this is your binary coming out of TensorFlow, this is your binary coming out of TensorRT. It does all sorts of layer combinations, and it minimizes your convolution sizes and does a whole bunch of interesting operations whose purpose is to give you a much smaller and much faster model with minimal loss in accuracy. But of course, that being said, your mileage may vary, and it's up to you to benchmark and make sure that this is applicable. And of course, we wouldn't be complete without mentioning the Mellanox stack. So I'm assuming everybody here heard about the acquisition, right? Complete silence. Yeah, so about 9 months ago, we announced the fact that we were buying Mellanox. And the reason for that is we can do all of that magic within the confines of a single machine, both software and hardware. But sometimes a single machine is simply not enough. Think autonomous vehicles, for instance, hundreds of petabytes of data that we now need to process. For that, we would need huge server farms, and the way to connect multiple DGX or DGX-like systems is by using network capabilities like InfiniBand, and this is where the Mellanox stack shines for various capabilities. Like some of the most important ones are all of the collective communications, which is the ability to do the same thing that we do for multi-GPU, allowing Horovod and similar frameworks to actually make best use of all communications channel across the network, regardless of it's within the machine or between machines. And this is another fascinating topic in its own right, and we would be happy to discuss this offline. So at this point, how are we for time? Yeah, so plenty of time left for questions if anybody has some. Yes?
Can you explain a little bit what Sharp is actually doing?
Yeah, so the question is, can you explain what Sharp is actually doing? So the answer, unfortunately, is not really. What I can tell you about Mellanox is that the ConnectX cards actually have this little microprocessor on them, so they're a computer all in its own right. And what it's able to do is offload a lot of the work from the network interface card. So it can do compression, it can do very low latency connections. It can basically do a lot of very, very smart network. It can do, think of it as compute that is oriented towards the network as opposed to neural networks. Let the GPU do neural networks, let the CPU do I/O, and let the Mellanox NIC focus on what's going on in the network and tune that. That's kind of like a very high level. I'm sorry, I really don't know what's going on under the hood.
So basically you're saying that we have another layer of hardware which actually performs also as a software, meaning that it performs some kind of calculations also, besides what the CPU does and the GPU, right?
So yeah, so there's another layer of hardware, and that's focused on network communications. That's software-defined X, right? Software SDX, software-defined anything. I think I just made up a term. Yes, anyone else? Yes.
They don't have a limitation on power. How does the T4 compare to, let's say, 2080 in terms of just inference performance?
Okay. So how does a T4 compare to a 2080? I'm going to generalize the question, and how does a Tesla compare to a GeForce? Right? So 2080 is a Turing card, but it's a consumer card. And T4 is a Tesla card. Although T is Turing, Tesla is the name of the product line. And Tesla cards are intended for data centers. So they can handle far longer periods of operation. So they're designed for 24/7 operation. They have much faster memory bandwidth. The driver is much stronger and able to do things like page retirement. So if you have messed up memory, if your memory fails, on a 2080, the card is gone. Okay, Tesla can then say, can do page retirement, can say this area of memory is simply not relevant. Software-wise, what you can do is you can run all sorts of policies on the Tesla. You can play with the frequency. So if you're limited, or if you have a budget for power or for heat or whatever, you can say that the T4 will not go above a certain amount of power. Or maybe after each job you wipe the memory. So there's a whole bunch of data center specific operations that are intended for the T4. And obviously it's supported much better. Something that maybe not a lot of people know is the fact that NVIDIA, apart from I think the Founders Edition, we don't make the GeForce cards. We only make the chip. And the actual cards come from companies like EVGA, Nsight, and so on. Teslas are produced by NVIDIA, and they're also guaranteed by NVIDIA. That's in a nutshell. Thank you.